In this lesson, we are going to talk about the definite integral. Now, in the previous section, we talked about finding the area under a curve by finding the sum of all the rectangles that we create with equal width under that curve. And then we moved that idea into what's called Riemann sums, and we said that the area under the curve was equal to the limit as n approaches infinity of this sum, where this was the width of all the rectangles, and this was the height of the rectangles, and then we added all of those up. This idea came with restrictions. In order to be able to use this, f of x needs to be continuous, and it needs to be non-negative. And unfortunately, that doesn't always happen. So now we're going to look at how we can apply this concept of the area under the curve to more functions using what's called the definite integral. So the definition for the definite integral says if f of x is a function defined on an interval a to b, the definite integral of f from a to b is given by, and then here's how it's defined. And that's provided that the limit exists. And if this limit exists, the function f of x is said to be integrable on the interval from a to b. Now, at the end of chapter 3, we discussed what's called the antiderivative. And we used this symbol for the antiderivative. And this was called an indefinite integral. Now, the difference between an indefinite integral and a definite integral is that the indefinite integral represents a family of functions. When we integrate f of x dx, what we're doing is we're finding the antiderivative, and remember, when we take that antiderivative, we get the function capital F of x plus some constant c. So this is a whole family of functions. Now, with the definite integral, we're on some interval from a to b. We're actually finding the area under the curve on that interval. So when we find that, we're actually finding the area under the curve on the interval from a to b. So this is going to represent a value, not a family of functions. You're actually going to get a numerical value for a definite integral. So to get familiar with the integral notation, this is your integral. And when we do this on an interval from a to b, that interval on a to b, that is called your limits of integration. This is your lower limit, and this is your upper limit. We call the function that we're integrating, that's called the integrand. And then the dx represents that the function is with respect to x. Which is also called the variable of integration. Now let's work through our first example, evaluating an integral using the definition. So this is the key. We're going to use the definition, and this is going to be a right endpoint approximation. Now, just like we found the derivatives using the definition way back when, and it was kind of long and drawn out, and then we found shortcuts. That's what we're going to do here. We're going to go through this the long way so you can see how it works, and then we can start using the shortcuts. So right now we're going to use the definition. And if you recall, the definition of a definite integral looks like this. We're going to take the limit as n approaches infinity of the Riemann sum and we're taking the limit as n goes to infinity because we want to take more and more and more rectangles so that we get the most accurate area that we possibly can. And so as n goes to infinity, we will get the exact area when we take that limit. So we need to set up first this Riemann sum. And then once we find the sum, we're going to take the limit as n goes to infinity. So the first thing that we're going to do is we are going to find our widths of each of the rectangles. So the width of the rectangle is going to be the length of the interval divided by the number of rectangles. So since we're on the interval from 0 to 2, that length of the interval is 2, and we're going to divide by n rectangles. We don't have a set number of rectangles here that we're dividing by because we're going to take the limit as n goes to infinity. So there's the width of our rectangle. So now what we need to do is we need to find the heights of our rectangle by finding the endpoints that we're plugging into the function. So now this tells us that we're going to use right endpoints. So if we imagine the interval 0 to 2 and we start thinking about splitting this up into rectangles, if I want to use endpoints that are on the right side of the rectangle, these are what I'm going to use. To find my first endpoint, my x1, that's going to be my starting point, which is 0 plus the width of the rectangle, because each of these is the width of the rectangle. When I find my second endpoint, so that's going to be this x1, when I find my second endpoint, I need to add another width of the rectangle. So that's going to be 0 plus 2 width of the rectangle. And I can simplify this since it's just 0 is delta x to delta x. If I want to find the third rectangle, that's going to be, I take my first point, which is 0, my endpoint, and I add that many delta x's. So it's going to be 3 delta x. So if I repeat this pattern, you can see that my xi's in general are going to be written as I times delta x. I can go ahead and substitute for delta x since we found up here that delta x is going to be 2 over n. So I can write this as 2i over n. Now that's what I'm going to plug in to my function. So my f of xi's in general are going to be 2i over n squared. When I simplify that, I'm going to get 4i squared over n squared. So we have our delta x, which we need that for the Riemann sum. We have our f of xi, we have that for our Riemann sum. So now let's set up our Riemann sum. So we have I is 1 to n, and we have f of xi times delta x. So when I plug in f of xi, I'm going to get 4i squared over n squared. That's my f of xi, and then times my delta x, which is 2 over n, and we're doing that from 1 to n. When I clean that up, I'm going to get 8i squared over n to the third. I'm going to finish up down here. Now, anything that doesn't have an I in it can be pulled out, right? Because we're plugging into the i's, right? When I is 1, we plug in 1 for I. When I is 2, then we plug in 2 for I. So anything that doesn't have an I in it can be factored out. So I'm going to factor out the 8 over n to the third. Now remember, from our previous section, we had a formula for this. So we have 8 over n to the third. And the formula for the sum of I squared, if you recall, is n times n plus 1 times 2n plus 1 all over 6. If you don't remember that formula, you can go back into your previous notes and check that out. Now, when I multiply everything out and clean this up, I'll let you guys do that. What you're going to get is 8 thirds plus 4 over n plus 8 over 6n squared. So this was equivalent to this. Now remember what our definition is. Once we get that, we have to take the limit as n approaches infinity. So I'm going to take the limit as n approaches infinity of 8 thirds plus 4 over n plus 8 over 6n squared. Now, as we start plugging in really big numbers as n approaches infinity, anything that has an n in the denominator is going to get super small and the limit's going to be 0. And what I'm left with is just 8 thirds. So what this means is, if I look at the graph of x squared on the interval from 0 to 2, the exact area under this graph that I'm shading in here in gray, we have just found to be 8 thirds. That's the area. So whatever the units are, if this was in the context of some kind of application and say the units were in feet, then the area would be feet squared. So whatever the units are, we're going to just write down units squared generically. In this next example, rather than using the lengthy definition of the integral, we're going to use geometric formulas to find a definite integral. So our function that we're going to integrate looks like this. And if you recall, this is going to be a semicircle. Remember from way back when, the equation of a circle looks like this. Where HK is the center of the circle. So if we play around with our formula here, if I square both sides is equal to 9 minus x minus 3 squared. If I add x minus 3 squared to both sides, I get x minus 3 squared plus y squared is equal to 9. So you can see that this represents a semicircle, and I say semicircle because it's only the positive square root. If I wanted the full circle, I would have to do the negative square root as well. But this is going to be a circle with a center of 3, 0, because that's my h and that's my k, and the radius is going to be 3, because remember, this constant here is the radius squared. So the radius is going to be 3. Now, if I wanted the full circle, when you look at the graph, the positive square root of 9 minus x minus 3 squared is going to look like this. I'll do it in pink. I'll highlight this in pink and color code it for you. My center is at 3, 0. If I did the negative square root, remember this negative in front here represents a reflection across the x-axis. So we would get the second half of the circle that looks like this. Since we're only looking at the positive square root though, I'm going to take out the negative square root function. Now, if we scroll back up and look at what we're supposed to integrate, we're supposed to integrate that function from 3 to 6. So what that means is we're trying to find the area under the curve, but above the x-axis on the interval from 3 to 6. So if my radius is 3, 6 is going to be here. So from 3 to 6 means I am trying to find this area here, which is a quarter of a circle. Since a circle is symmetric, all I have to do is find the area of the full circle and divide it by 4. If you remember, the area of a full circle is pi r squared. So if I want to find a quarter of this circle, I take a fourth of the area, and I'll have the area that's shaded in gray, a quarter of that circle on the interval from 3 to 6. So I'm going to take 1/4 times pi times 3 and square it. That's going to give me 9/4 pi. Now, if I put that in a decimal format, that's going to give me approximately 7.069. So what this means is, if I were to integrate from 3 to 6, the square root of 9 minus x minus 3 squared dx, the value of this would be, if it's exact, I would write 9/4 pi. If I want to approximate it as a decimal, I would write it as 7.069. So that tells me what that gray shaded area means on that interval from 3 to 6 under the curve, but over the x-axis. So this is the difference between an indefinite integral and a definite integral. An indefinite integral just represents a family of functions, an antiderivative, where a definite integral is going to actually give you a numerical value when you're looking at a specific interval. Now we're going to talk about the difference between a net signed area and a total area. If I look at some generic function, let's say I look at a function that looks like this. I'm going to color code this for you. I'm going to call the green area 1, and I'll call the pink area 2. When we integrate, the area that is above the x-axis, so in this specific case, area 1, that area is going to be considered positive. And when we look at area 2, that falls below the x-axis, that area is going to be considered negative, less than 0. So when we integrate, if the area 1, let's say the area 1 is, let's say 2, and let's say area 2 is -5. The area is 5, but because it falls below the x-axis, it's going to be -5. So when I integrate this function from a to b, I'm going to end up getting an area that's -3 because I have more area that's below the x-axis. And that's considered the net area. Now, if I want the total area, I'm not going to consider whether it's above or below the x-axis, whether it's considered a positive or a negative area. Let me draw a separate picture for this. I'll do the total area over here. We're going to look at the absolute value of those areas. I'm not going to consider whether it's negative or positive. It's just all going to be positive. So when I draw the picture of the absolute value of this function, it's going to look like this. Because that area 2 gets flipped up and becomes positive. So this pink area is now above the x-axis and it's positive 5. This green area, which was A1, which was positive 2, now the total area will give me 7 because I'm taking the absolute value of that area. So this integral would be 7, where I'm doing the absolute value from A to B, whereas the net area, using this example here, would give me -3 because I take into consideration what area is above and below the x-axis. So now we're going to walk through an example of finding the net signed area. We are also going to go through, even though the question doesn't ask for it, how to find the total area with this same problem. So the question is asking about finding the area on the interval from -3 to 3 for the function 2x. So if I graph the function 2x, it's just a line that comes up through the origin. And if we're going to do this on the interval from -3 to +3, we need to know what the corresponding y value is. This would be 6, and this would be -6. Now, if we want to find the area between the curve and the x-axis on this interval, we're looking at this area here. We'll call that A1. And then we have this area here from -3 to 0. We'll call that A2. Now these are just triangles, so to find area 1, we're going to take 1/2 the base times the height. The base is 3, and the height is 6. So when we work that out, we're going to get that the area is 9. Now, because it's above the x-axis and we're doing the net signed area, this is going to be specifically a +9. Now, when I look for area 2, again, that's a triangle, so we're going to use 1/2 base times the height to find that area. And again, the base is 3 and the height is 6, but because it's below the x-axis, that is going to give us an area of -9. So if I were to find the integral from -3 to 3 of 2x dx, that net signed area would give me 0, because if I take the positive area 9 and the negative area, which is also 9, and we get 9 and a -9, that gives me 0. So this would be considered the net signed area. Now, if I want to find the total area from -3 to 3, and I don't want to consider the fact that it's above or below the axis, I want to take the absolute value of our function and integrate it from -3 to 3. And when we don't consider the signed values, if I have 9 and 9, that's going to give me 18. So this would be considered the total area. Now the picture for that, if we flip this negative area up and take the absolute value, now my green area becomes positive because it's above the x-axis, and we have a +9 area. So then I would take +9 for, we'll call this area 3, and we would have a +9 for area 1, and when I add those up, I would get a +18. So that's the difference between the net and the total area. And the reason why it's considered negative when it's under the x-axis is because remember how we calculate the areas of those rectangles. To find the height of those rectangles, we use the value of the function at those endpoints. And if we look at the value of the function when we're below the x-axis is going to be negative. So when then we take a negative number times the width of the rectangle, that's going to end up giving us a negative area. In this example, we're asked to find the total area. However, like we did in the last example, I'm going to find the total area and the net area just for practice. So the function that we need to find the total area for is x minus 2. So the picture is going to look something like this. Here's my graph of x minus 2. Now we have to do this on the interval from 0 to 6. So here's 0, and here's 6. So we need to find this area here. We'll call that area 1. And then we need to find this area here, which is area 2. Now these are just triangles again. So to find area 1, we're going to take 1/2 the base times the height. And that's going to be 1/2. Now this point here where it crosses, the x-intercept is 2. So my base for that triangle for area 1 is going to be 4, right? From 2 to 6, that's a length of 4. And then my height, x6, is going to be 4, my corresponding y value. So I know my height is 4. And so I'm going to get an area for 1, which is 8. Now for area 2, it's the same thing. We have 1/2 base times height. Right here where it crosses the y-axis is -2. So this length from here to here is 2, and this length from here to here is 2 as well. So when I plug that into my formula, I have 1/2 times 2 for my base and times 2 for my height. And I'm going to get that the area of that triangle is 2. Now if we find the net area from 0 to 6, this is what our integral will look like. And that will give us an area of 6 because 8 is considered positive and area 2 is below the x-axis, so that's going to give me a -2 area. So if I have an 8 and a -2, that's going to give me a net area of 6. Now if I find the total area, I'm going to set up my integral like this from 0 to 6, but now I'm going to use the absolute value, and that is going to give me a total area of 10 because I have 8 for the first area, 2 for the second area, and I total that up and I get 10. Now the picture for the total will look like this. If I flip it up, to find the absolute value, then my new area for area 2, we'll call it now area 3, that's going to be this. That's going to be a positive area of 2. So that's what my picture would look like if I take the absolute value. That gets flipped up. So we have a net area of 6 and a total area of 10. Okay, now let's look at the properties of integrals. This applies to indefinite and definite integrals. And later we're going to use these to manipulate expressions to evaluate the integrals with the shortcut method. Okay, so the first property says if the limits of the integration are the same, then the integral is just a line and it contains no area. So notice my limits of integration is the same point. So if I'm looking at a function, let's say the function is x squared. If I look at an area under the curve at just one point, from A to A, there's no area under that curve. It's just a line. The area from A to A would be 0. The second property says if the limits are reversed, then the sign of the integral gets swapped. So notice the limits of the integration in the first integral here is from b to a. If I switch the order of those and go from a to b, then I just have to put a negative sign in front of that integral. The sign just gets reversed. The next property says the integral of a sum is the sum of the integrals. And that works. These two are basically the same. It just says that if you are taking the integral of the sum or the difference of two functions, you can write it separately. Instead of writing the integral from a to b of f of x plus g of x, you can write it as two separate integrals. So whether that's plus, I can separate it with the plus, or whether that's minus, I can separate it with the minus. The next property of integral says if I have a constant in front of the function, I can pull that on the outside of the integral. So if I take the integral of some constant times a function, that's the same thing as taking that constant times the integral of the function. And lastly, we have this property where it says if you have a value of c between a and b for your limits, then you can break it up into two integrals, and this is what the picture would look like. If I have, let's just use x squared again as our example. If I have a to b, if I have that interval, and then I have a c in between, I could write the integral from a to b to find the entire area at once of x squared, or I can break it up into two intervals. I can say I'm going to take the interval from a to c, and add it to the integral from c to b. And I can find those two areas separately and add them up, and that will give me the same as the integral from a to b. So in this example, we're going to use the properties of the definite integral, and we're going to rewrite the definite integral of f of x is equal to negative 3x to the third plus 2x plus 2 over the interval from negative 2 to 1 as the sum of three definite integrals. There's my lower limit from negative 2. Here's my upper limit to 1. And then I have my function, which is negative 3x to the third plus 2x plus 2 dx. And I'm going to rewrite that as three different integrals because I have three terms here. So think of this as three different functions that I'm adding together. So I can rewrite that as the integral from negative 2 to 1 of negative 3x to the third dx plus the integral from negative 2 to 1 of 2x dx plus the integral of 2 dx from negative 2 to 1. Now I can also rewrite this by pulling out my constants in front of my function. So I can rewrite this first integral, negative 2 to 1 of negative 3 times x to the third, and then dx. I can pull that 2 out in front and write it from negative 2 to 1 of 2 on the outside, and then x dx. So I can take those constants, this one, and pull them on the outside. In this next example, we're going to use another property of integrals. Recall that we have a property that if we have some function f of x and we're on an interval from a to b and we have some value of c in between, we can take the entire interval from a to b and integrate, or we can separate it in two intervals and go from a to c and then from c to b and integrate and add them together. So in this question, we have a function f of x, And we're looking at the interval from 0 to 8. But there's a break in this interval. There's a 0.5 in between. We are given the area under the curve from 0 to 8, the entire interval. And then we're also given the area under the curve from 0 to 5. And we're asked to find the integral from 5 to 8. So using that property, we know that the integral from 0 to 8 of f of x dx can be written as the integral from 0 to 5 of f of x dx plus the integral from 5 to 8 of f of x dx. So if I call this area 1, and if I call this second area from 5 to 8 area 2, the total area from 0 to 8 is area 1 plus area 2. Since we're given that the integral of the whole entire area is 10, I'm going to replace the integral from 0 to 8 of f of x dx with 10. We're also given the integral from 0 to 5, that area is 5. And what we're trying to find is the area under the curve from 5 to 8. So just using some basic subtraction, if I subtract 5 from both sides, I know that my area from 5 to 8 is going to be 5. Because we have this area plus 5 has to be equal to 10. So that integral from 5 to 8 of f of x has to be 5. Now let's take a look at the comparison theorem, or 3 items to look at for the comparison theorem. The first item says, if the function is positive on the interval from a to b, then the area from a to b is going to be positive. The second part to this theorem says, if the function f of x is greater than the function g of x on the interval from a to b, then the area under the curve of f of x on the interval from a to b is going to be greater than the area under the curve from a to b of g of x. And then the last part of this theorem says, if m and m are constant such that the value of the function falls between little m and big M on the interval from a to b, then if you take the difference of the interval and multiply it by little m and big M, the area under the curve from a to b is going to fall between those two values. So to get a picture of what that looks like, if we have some generic function f of x from some interval, on some interval from a to b, and the y values, or the corresponding y values for f of x falls between little m and big M, then the area under the curve on that interval is going to fall between the two values that you get when you take little m times the length of the interval from a to b and the length of a to b times big M. So let's take a look at the next example and compare the two functions over a given interval. So we have the function f of x, which is the square root of 1 plus x squared, and that's in orange. And then we have g of x, which is the square root of 1 plus x, and that's in blue. And we're looking at this specifically just on the interval from 0 to 1. So we're looking at just on this interval right here from 0 to 1. Now, it's kind of hard to see what's going on in that area because the graphs of f of x and g of x are so close together. So if we zoom in, that would be in the picture B. If we zoom in, we can see that g of x is above f of x on the interval from 0 to 1. Here's 0, here's 1. So that means g of x is greater than or equal to f of x on the interval AB. So what that tells us is that the area under the curve for g of x from a to b is going to be greater than the area under the curve of f of x from a to b. Now, if we look at that, I'm going to try to use two different colors here. If I shade everything under the graph of g of x, that's this area. Now, I'm going to erase that. And now I'm going to shade everything underneath f of x. This is the area in which g of x is bigger by, because it has that extra area when you look at that interval from 0 to 1. In this last topic of our lesson, we're going to talk about the average value of a function. And there's a lot of times we want to find the average of something. But in order to find the average value of a function, what we're going to have to do is we need to take the area of the function on the interval from a to b, and we're going to divide it by the length of the interval. And that will give us the average value of the function on that interval from a to b. Now, in order for this to work, you have to have the requirement that the function is continuous on that interval. So let's go ahead and apply it in this example down here. So the question says, find the average value of the function f of x is equal to x plus 1 over the interval from 0 to 5. So here's our picture. If we have the graph of x plus 1, it's going to look something like this, just a rough sketch. It's going to cross the y-axis at 1. And the corresponding y value at 5 is going to be 6. So we are looking for this area here, shaded in pink, to find the average value of the function. We need to find that area and then divide it by the length of that interval. Now, if we want to find the area under that curve from 0 to 5, we're going to have to break this up into two pieces. So I'm going to call this top area, area 1, and this bottom area 2. So the top area is the area of a triangle, and this height is 5 because we're going to go from 1 to 6, which is a height of 5. And then the base is going to be 5 because we're from 0 to 5 for the base. So area 1 is going to have an area of 1/2 base times height, which is 5 times 5. And then we're going to add it to area 2, which is just a rectangle. And the area of a rectangle is length times width. Now the width is 1. And the length is 5, so we're going to have, for area 2, length times width, which is 1 times 5. When we add that up, we're going to get an area of 17.5. And then that's units squared. Whatever the units are, we're going to square them. So we know that the area under the curve from 0 to 5, the total area is 17.5. Now, to find the average of the function, we're going to take the area and divide it by the length of the interval. So if we're going from 0 to 5, the length of that interval is 5. And so we're going to get 3.5. So what this means is on the interval from 0 to 5, the average value of the function is 3.5.